inviting me from Berlin to here. So I'm very happy to give a talk by coming back again. And yes, so I'm talking about some algorithms on graphs of bounded trees, which generalize some very recent result on the feedback vertex. So we define a new problem and then we give us some algorithmic application. So this is joint work with Edward Bonnet, Nick Brettel, who were postdoc at the same time with me, and Daniel Max. So the talk will consist of 3 parts. So I will give a definition of treewidth and maybe to remind all who don't know the definition of treewidth. And then the main half of the part will consist of explaining what is the representative set. So maybe the treewidth is already good for obtaining some algorithm, but maybe naive algorithm doesn't give a very optimal algorithm. So then people try to think about how to reduce the algorithms and how to reduce the running time of the algorithm. And then recently the people give us some definition of the representative set and applications. So representative set actually came from very long time ago, but recently adapted to treewidth. And the main focus, I will mainly focus on the feedback vertex set algorithm, so I will explain a little bit on this. And then we try to push this algorithm, this running time for feedback vertex set to the more generalized problem. And then we obtain, for some cases, we say that we can also obtain this kind of running time, but sometimes it's not. So we give us some dichotomy results. So I will give this.
Is W the treewidth?
Yeah, W is a treewidth. Yes, on treewidth W. Yeah. Yes. So most of the slides that W denote the treewidth. Yes. So the definition of the treewidth is maybe you're already familiar with this. So if you have a graph, then the tree decomposition looks like this, where you have a tree, and then for each node you assign some vertex set of the graph, satisfying the 3 property that this vertex set, the union should cover the whole vertex of the graph, and every edge of the graph should be contained in some bag. So we call this, each part is a bag. And for each vertex in the graph, the bags containing this particular vertex should be connected in this tree. So this is definition. And the treewidth measured how we can decompose it into small bags as possible. So the definition is the minimum integer such that G has a 3 decomposition of width and most W plus. Each bag has size and most W plus 1. But probably you don't get any intuition how to apply for this 3 decomposition on some problem. So maybe I give another equivalent definition. So you have so the boundary graph is a pair of a graph and vertex subset like G and S, like this picture. And especially if this boundary has at most W vertices, I will say that W boundary graph. Okay. So boundary will denote by D of G. And I will give a four. Yes. So this is just notation. So I will call this special vertices as boundary.
The letter G as a W boundary, right? G is used for 2 meanings, right?
Yes.
It's a pair of G and S.
Yes. So I should say G and S here, but usually I skip this. Yes. Maybe I.
G, S.
Yeah, G, S. Yes. Right. Yeah, I want to skip the S in the notation. So yeah. Okay, so I will define 4 operations, how to construct some new boundary graph from some another boundary graph. Like first trivial operation is that you introduce a vertex with own boundary. So I will put the red circle for boundary vertex. And the other is that you introduce a new vertex where all neighbors are contained in the previous boundary. So like this is a new vertex. So I will add this vertex, and then neighbors should be contained in the previous boundary. Does it make sense? And then, so I will also say that this new guy is a boundary. So this is one operation. And the other operation is that you just have a same graph, but you forget about, so you replace the boundary vertex with a non-boundary vertex. And the last one is that, so you have two boundary graphs where these two boundaries have a same graph, then you merge this along the boundary like this. You take a disjoint union and then identify each vertex. So for instance, like if I want to create this graph, then maybe I can create like this. So you introduce this vertex with a boundary, and then you put the new vertex like this, and then you forget that this is a boundary. And then also you create like this to create the same graph, and then you merge these two graphs by a boundary, right? And then in the last step, you add a vertex to this boundary. Then the point is that this tree can be constructed by only two boundary graphs, right? Yes.
Can you go back a little bit?
In the
Yes. So the operation operation 2 can be omitted, right? Because you can introduce a graph and then you can use 1 and 4. Right?
Yes, yes, maybe that's true. Yes.
But so these boundaries should be cliques?
No, not necessary. Yeah, this is special. Yes. So yes, right. You make a triangle to do this, right?
Yeah.
Maybe.
First make a triangle and then glue them by operation 4.
Yes, that's true. Yes.
So if we delete the first condition, then does it mean Technische?
If you remove the first guy?
No, the last one.
The last one. Probably not. Maybe. Yes, maybe that's true. Because whenever you add a vertex, you apply this operation. I think so. Yes.
Number 2b has only neighbors in S. It doesn't have to be neighbor to everybody in S. Right?
Yes, new vertex.
Yeah, I see. Okay.
Then how do you make? Then is it really the same? Because if you use only 1 and 4, that means the boundary size must be the same.
No, you don't have to use all.
Yes, so you don't need to add all the guys. So you may add something.
But 4 says the boundary sizes must be the same when you identify.
Yes, that's true. You create the same graph with these two boundaries. Okay, so maybe, yes, makes sense, right? Because this operation, this remain as a boundary. But if you merge with the triangle, then you should forget about this as a boundary.
The boundary size changes for 2, but if you keep on doing 4, the boundary size
I see.
don't
So
change.
you need some operation to increase the boundary.
Yes, that's true.
Right.
Yes, that's
Yeah, okay.
yes, I also mixed up. Okay. And then in general situation, you have some tree. This construction scheme give us some tree structure like this. So you introduce some nodes and then you add boundaries and you join and then forget something, and so on. And you can easily recognize that every graph has tree width at most W if and only if you can construct using only W+1 bounded graphs. So the previous example says that trees have tree width at most 1 because you can construct it only using 2 bounded graphs. And also if you think about the cycle a little bit, then you see that cycle have tree width 2. But maybe cycle have tree width more than 1, so you can confirm this. So how to adapt this tree width to the algorithms? So like a 3 coloring problem asks whether a given graph can be properly colored by 3 colors. And this is NP-hard. What I want to do is that, so at each point, you have some bounded graph, right? And then I ask whether, so I first guess some colorings on the boundary. So like, let's say this guy red and this guy green and this guy blue. But the number of boundaries are at most the W+1, if tree width is W. So you have only 3 to the W+1 options on the boundary, right? And then for each boundary, so I ask whether there is some 3 coloring of the whole graph where the discoloring projects to this boundary, actually this coloring. This is easy to determine because so you go back to the previous graph and then you just ask whether there is a coloring for extending these 2 coloring, and then you just confirm that blue, red, green is fine for this triangle, right? Because the important fact is that this vertex doesn't have any neighbors on the other part, right? So you can easily update this algorithm. So this means that you can solve this 3 coloring in time 3 to the W. So 3 to the W from this guessing the boundary, and on graphs of tree with W. Recently, under some hardness assumption, the Nokstanov, Max Zaurab showed that you cannot improve the 3 minus epsilon to the W. But this is SETH is strong exponential time hypothesis. But I don't want to explain. But there is some hardness assumption like this. Maybe I can explain you if you want later. Okay, so but what I want to focus is that the more difficult problem, like coloring is like a locally checkable problem where the coloring is fine or not is you can just look at every edge, right? So but the feedback vertex problem is the more some connectivity problem. So the problem asks the objective of problem is that find the minimum vertex set S such that G minus S is a forest, or maybe G minus S has no cycles equivalent. And if you think about what are the partial solutions, so in the whole graph you have some deletion set, and then say the remaining is a forest. Then if you look at the current graph, then this solution should intersect like this. So you have some set to delete in the boundary, and then some set to delete in the inside, and then the remaining forest, right? So this will be some partial solution, but of course keeping all of this information would be redundant, right? So what the important information is that actually the size of this Y, because once I remove this, then information what exactly vertices in Y1 is not really important, right? So I want to keep the size of the Y. And also the redundant thing is that like these 2 graphs have a different forest, but the connectivity between the 2 vertices on the boundary are same, right? This guy and this guy are connected by below, and then here also this guy are connected, right? Actually, this is all that I need to import, store, because if there is something and then merging with this guy is a forest or not, actually determined by this connectivity between the 2. Like if these 2 guys are connected like this, and then you have a cycle, but then you also have a cycle in here, right? So this is something or information that I want to keep. And then, sorry, in the actual situation, you get something to delete on the boundary. So for this, I keep the exact vertex set, but this is 2 to the size of the boundary, right? And then the L is the number of delete in the inside. And then the partition of the boundary delete X, where this partition means that the same part give a they are in the same connected component in the remaining for list. So I put this C of T X L P to 1 if there is a realization of this. Right? There is some Y inside of size L such that GT minus X union Y is a forest where the connectivity condition gives this partition P, right? And then I put the 0 if there is no such realizations.
So the size is precisely now?
Yeah, precisely, because I will go through all the integers. The question is that can we recursively update? But like a 3 coloring, you can see that it's not really difficult. Right? Okay, so I will keep to you this. And the point is, okay, so this was already known very, very before. So like people just try to think about, and this is a really naive way to do it. But then, so you can see that if you just run like this, then the number of partitions should be a problem, right? So you will go through all partitions of this size of W set. So this might be a 2 to the W log W set. And so this gave us some naive running time that 2 to the order of W log W times polynomial n. So then the people, so it's a long time, the open problem that this can be reduced to the 2 to the order of W times. So you can remove this log W term. So then this representative set technique appears. So when I visited Hans Boder, and he explained about this. Okay, so in the original paper, there is some first type, but I will remodeling this representative set again. So, but I will give a first one again in the first type. So U is some underlying set, and then you consider 2 partitions of the in this underlying set, and then we say that P sum Q as the common coordinating of these 2 partitions with the maximum parts. What does it mean? Is that like P is like this and Q is that, then maybe just the one part with 1, 2, 3, 4 is also a common coordinating. So coordinating is by obtaining some merging some parts. And refinement is that you split the part to some other things. So like if you merge these 2 guys to the one set, then this is coordinating of this guy. So, and maybe, so trivially, if you merge all the guys, then you have a common coordinating, but this is common coordinating with the maximum parts. Right? So trivially, so this should be unique. And our question is, so the question is that you have some sets of partitions, A, and you have another set of partition, B. And then I want to find some subset A prime of A satisfying this property, where this property is that whenever you have a P in A and Q in B, where P sum Q generate just one partition with the whole guys, then you have some P prime in A prime with the same property. But then size, I have a size restriction that A prime, the total size is bounded by 2 to the order of U. I should put this size U here. Okay, so such a set A prime is called the type 1 representative set of A with B. So can you find this? And what they show is that you can really find such a set. Actually, in time, this A is the size of the given set, and then U is the underlying set, right? So this is a matrix represent this. Like you have these partitions on the 4 elements, and then if you have this elements and this element, and then union, the sum gives the whole partition, so sum gives so whole things as a one part. Then I put the 1, and then 0 otherwise, right? Like this guy is already connected, so right, you put the all of 1. But maybe this guy and this guy, the sum just still doesn't connect it, right? And then the important information is that you can find, so if you consider this as an A, so you want to choose some A prime among them, satisfying the previous property. Like this is related to rank of the matrix over the binary field, because what I want to do is that, let's say this is A prime, then whenever you have a 1 in here, you should have a 1 in here, right? This means that, so if this is a basis of the matrix, then this satisfies the property. Because if you have a 1 here, then this vector should be generated by a sum of this guy, then one of them should be 1, right? If all of them 0, then you cannot generate 1 here, right? So it's sufficient to find some basis of this matrix. And then the Baudelaire there use this technique that, so first observe that the P sum Q generate this partition if and only if the number of all common coordinates is odd. Because okay, maybe this is not true. Okay, yes, sorry. So I wanted to remove this, but maybe you can forget about this. And what they do is that so you introduce a new matrix C, where the rows are indexed by some A. So rows are the same, but columns are indexed by partitions of the U. Instead of the whole partitions, you introduce the bipartitions of the U, and then you put this C, P of B is 1 if P is a refinement of B. In other way, so B is the coordinate of P. And then this is very easy to see that the M and C transpose have same up to modulo 2. And then using this, but this C matrix, the columns are at most 2 to the size of U, because you only have bipartitions, right? So the rank is bound. This rank of the matrix C is bounded. So you can use this to find this A prime. Okay, but what I want to say is that so this approach directly applied to some problems like a Hamiltonian cycle or Steiner tree problem. But for feedback vertex sets, so this is technical. So, but what they do is that they modify some graph in the very different way, and then they apply this technique to feedback vertex set algorithm in the original paper. But actually, we can do some general way. Like I introduced another type of representative set using this technique. So you have a hypergraph V and E. So E is just a set of subsets of V. And so I define an incidence bipartite graph where you have a vertex and then edge sets, and then you put the edge if the vertex is included in the edge, like this. And we say that this hypergraph is acyclic if this incidence graph has no cycles. Okay. So then we have the same question like as before. You have a set of partitions, and then I want to ask whether there is some A prime in A with a size bounded by 2 to the order of U, where the P union Q generate a cyclic hypergraph. Then there is a P prime in A prime with the same property, right? I will consider U as a vertex set, and then P union Q as a edge set on the hypergraph. And then we call this a type 2 representative set. And this actually can be obtained as a corollary of the first result. So what I want to do is that actually I want to relate the acyclicity of this hypergraph into the sum of two partitions are the whole things. So for this, I observe this property that okay, when I have this partition P, so I say this is a one cosigning P, where one cosine means that you just merge it to create the one U set. Like this is one cosigning of this guy, but this guy is not a one cosigning because you have a new two sets, right? The observation is that if you have a P and Q where P union Q is acyclic, then there is a one cosigning P prime of P such that P prime union Q make a connected hypergraph and acyclic. So if you have a cyclic and it's not connected, then you just merge a sum of the parts to make a connected. And then the other observation is that if two partitions already make a connected, then this is a cyclic if and only if you have this size constraint, because connected acyclic graph is 3, right? So you have this simple observation. And then the algorithm just run like this. So you have a given set A, and you generate all one cosigning from this partition. But one cosigning has a bounded size because for each fixed partition, you only have 2 to the, but actually the number of partition is not really important. And then, so from A prime, so you divide up to the size of the parts. So A1 is this partitions in A prime with 1 parts, and A2 is 2 with 2 parts, and so on. And then I forget about the original B, so I just consider the BI as a set of all partitions of the U with the number of parts is exactly I. And then I obtain a type 1 representative set R of I from AI with respect to this size. So what I want to do is that just I plus this is S plus 1, so that the sum of these two guys actually make a cyclic hypergraph. And then we take a union of all of these guys, then this gives a representative set for type 2 representative. So the size actually blow up by S, but R is a type 2 representative set. So this is one thing that I prove in the paper, but actually some simple observation from the previous. And then we can obtain this, we can reduce the running time to the 2 to the order of W by recursively enumerate the representative set of the set of partitions. So instead of keeping 1 and 0, just I keep all the partitions that satisfy some configuration on the X and the number of deleting to set in the inside, and then we put the representative set for this set of partitions, and then we update these sets again and again. So then you can see that you can obtain this running time. Is there some question so far? Okay, so I want to use this tool to some more general problems. So this is what they call generalized vertex set. So for this, I will need this notion of a block. So block, so two so okay, so cup vertex is a vertex that make disconnected. And so block is the maximal connected subgraph in the graph that does not contain the cup vertex. Like this so this subgraph is a block, but if you add something on this, then you suddenly have a cup vertex. So it's not a block. But block may be like an edge because this cannot be extended to some other as well. So you can easily see the Fourier star graphs where every block has at most 2 vertices. So like a simplest one. So we just ask whether then you have some other constraint D where you want to find the deletion set S such that each block of G delete S has at most D vertices. And then actually I have a previous work and then it's on the appeared on the WG this year that we have some running time of the algorithm and parameterized by a deletion set as well, size of the deletion set as a K. And then this can be solved in time to the order of K log D times polynomial N, but you cannot improve this strictly faster than small of K log D. But there are 2 constraints, so maybe some functions maybe not comparable to the K log D. But if you have like you cannot have a 2 to the small of K log D or something like that. And so also WM hard parameterized by only W or T or only K or D. So main open problem in this paper was that can we have some running time of 2 to the order of K plus D. So K plus D is not comparable to the K log D. It depends on the K is much bigger than D or D is much bigger than K or something. And so the obvious thing is that if the yes instance should have tree with K plus D, right? So you want to delete K vertices to make each block has at most D vertices. So tree width is like a D minus 1 actually. But whenever you add a vertex, the tree width increases by only 1. But then maybe we can use the algorithm for tree width to obtain this running time, right? But actually, this seems also difficult. But this doesn't say that this open problem is not true. But this is an interesting problem. And go back to this original problem, and then so we ask whether for whenever you fix D, like for feedback vertex that is D is fixed as 2, right? But here I just fix the D as a constant, and then I want to obtain this running time. But actually, we show that this cannot be possible in general. So I mean that you cannot solve in time to the small of W log W even for fixed D. But then, what we want to do is that we want to push this really nice algorithm for feedback vertex, right? Maybe some of them is possible, and then we introduce a new problem. And this might be a very technical, but maybe for us this was very interesting. So we have some class of graphs P, and you want to find the deletion set so that each block in the G minus S is in P and has at most D vertices. So you have a constraint on this property of this block. And obviously, this P is a class of all graphs, then this is the same as before, right? Okay, so what he did is that, so if P only consists of Kodal graphs, then you have this running time. But if you want to have some induced cycle of length and it's 4, then you cannot have this. So Kodal graph is graph having no cycle of length and is 4 as an induced subgraph. And then we have some trivial assumption that we say the P is block hereditary if a graph is P and H is a two connected subgraph of G, then H is P. And also we assume that we recognize every in polynomial time. Yes. So Kodak graphs are actually closely related to tree width because it's known that the graph has tree width at most k if and only if this can be embedded into Kodak graphs with the maximum click size k plus. So that is maybe the reason why Kodak graphs really work for this running time. But if you want to have an induced cycle, then this might be a problem. Okay. So I've given a very brief, maybe some ideas on how to prove this. Like partial solutions look like this, right? So you have, like a feedback vertex set, so you want to delete something on the boundary, and then you want to delete something on the inside. So I store this as some integer, and then I store x as a precise vertex. And then the remaining thing is a graph where each block has at most d vertices and is in P. So here you have some blocks, right? So like this triangle, or maybe some blocks are inside in the graph, right? So this might be technical. So one observation is that, so look at the two vertices in the boundary, and if they are contained in the same block, then this should be the same block in the last graph, right? So if they are contained in block, then this should be a block in the final graph. So what he did is that we just guessed the final shape of the block for this particular block. But this is bounded because we restrict the size of this guy, right? So because all the target graphs are the graphs of size at most d, and then it's in P, right? So this should be a 2 to the order of d square. And then we just guess for each block on this boundary, so we guess the final shape of this thing. But maybe the two blocks are currently in the distinct block, but maybe they are in the same block in the final shape. So then we need to keep all the things inside. So this is my question. And then this picture actually says that if you once decide to store every information, then the information might be a 2 to the w log w. What this picture describes is that so this is a boundary, and then this is some inside, and then I want to keep that this guy is some part of some block, 1, 2, 3, 4, and they are all the same. So actually, I don't need to keep anything for the blocks, right? There is no block on the boundary, right? But even though, so you might have some this kind of connections, which may be bad for obtaining 2 to the order of w. But for Kodak graphs, you have a nice property of this. So this is very easy observation that you have a Kodak graph and you have some vertex separator to divide it into connected components. Then actually there is a one-to-one mapping between you look at the neighborhood of this set. Neighborhood means that the set of all vertices having a neighbor on this separator. And then this might have a connected components, right? So this is actually one-to-one corresponding, there is a one-to-one correspondence with the set of all components in the whole graph, right? So this is not true in the general graph, right? Because you imagine the grid and then you pick a vertex, and then there are 4 neighbors, but in the whole graph, there are only 1 component, right? But Kodak graph, this is not possible because if you have a path like this, then you can create the induced cycle. Actually, this separator should be connected, but yeah. So I just, I don't need to keep the all information in the inside, but I just keep the which neighbors are in the inside or not. So this is sufficient to do this. Like what I did is look at this edge. So this edge is a block, and then for this edge, like I guess the final shape of this. And then you have this vertex for the inside. So I just say that this guy has this one vertex as a neighbors. So maybe this is not very useful, but maybe if you have these whole things in the inside, then I don't say that the whole things are inside. I just say that these two neighbors are inside. So I don't need to store all the information for the whole graphs. Yes, so yes, this is all the thing. And then what we prove is that you have two partial solutions, and then so there is some outside where you create the Kodal graph, and then each block make really block what I guess. Then the other one also generate the same property. So this is quite technical statement. So I skip the really the detail. Yeah, but for this statement, I assume that they generate the Kodal graph. Maybe so one didn't generate the Kodal graph, then equivalence might be different, right? For instance, if you have these two partial solutions, and then the blocks informations are same because this guy has this triangle block and this guy also have triangle block. Maybe so we have same information for these two blocks. But this guy are connected like this, and this guy is not connected to this. So they shouldn't be equivalent, right? Because here you have something like this, then you create some long induced cycle, right? Maybe this is more than D, right? So then it's problem. But if you have something like this, then this doesn't create any problem, right? So so you need to determine whether it generates the Kodal graphs or not. And this is related to the partitions of the set of connected components on the boundary. So they are connected via inside or not. And then using the representative set, you can avoid to blow up this to the 2 to the double O double. So this is the algorithm. And then maybe I shortly give how to obtain the low bound. So it's interesting that if you have an induced cycle in the P, then you cannot obtain single exponential algorithm, right? So maybe I shortly say that. So if you consider this as boundary, so if you, as I said, if you don't have if you only have a Kodal graph in the list, then you look at each boundary, and then it's sufficient to. So this is inside graph. Then it's sufficient to see that what are in the neighbors. You don't need to see the whole inside. But if you in the P you have an induced cycle, then you need to keep something more because there is a possibility to generate an induced cycle in the future. So like if you have like this, then this might create the induced cycle, which is fine. So you need to keep some more information if you have an induced cycle in the list. So then formally we prove by this technique. So exponential time hypothesis is some hardness assumption, and it says that m variable 3 set cannot be solved in time 2 to the smaller of n. And Rokstanov and Max Sarab proved that if ETH is true, then permutation k by k independent set cannot be solved in the 2 to the small of k log k. So what is a permutation k by k independent set? So you have a k by k points, and then so you want to find the independent set where each column has one vertex per one vertex. But if you don't have this permutation, this is just says that you find the independent set where each column has one vertex. But permutation means that you also have one vertex per each row. So we can reduce the from the permutation k by k independent set. So the gadget looks like this. Very briefly, so okay, so I have this k by k graph. So you have some edges, right? And then in the whole picture, it looks like you make some gadget for each edge. E1, and you have E2, and so on. And then you have some connector for selecting, this is for row, and then this is for column, and then, and so on. So you have one column for each edge, but so this tree width is bounded because these guys are small, so after removing this, you have some bounded tree width. So this is the picture. And so the construction is that, for each column, so you have some gadget for each vertex. So this is for each vertex, and then this generates some same row. And yes, I will skip the detail. But what it proves is that k by k independent set has some solution if and only if you need to delete most of them except this corresponding independent set. Then you will remain some size cycles of length exactly at each point. Okay, so this is most of the part. So we have a dichotomy result for generalized feedback vertex problem. And maybe I have a question on this, but I didn't look at very carefully. But maybe some other problems like here, so we want to restrict the size of the block. But like we also have a result for the size of the connected components. So this is generalized vertex cover, but this is rather simpler than feedback vertex. But what if we want to have components where each component has a diameter at most d or something like that? Then, so if you have a Caudal graphs, you can easily do or something like that, or other properties. And I want to mention that with Mamadou Kante and Benjamin Borgonox, who is a student of Kante, and when I visited him, so there is an open problem for Hamiltonian cycle for Klieg's bounded graph. And so the Fominator has a paper on this, and then they show that there is no n to the small of k running time for Hamiltonian cycle under ETH, but the naive algorithm is n to the O of k square. So the question was that is there an algorithm to the n to the order of k, and then we devise some new type of representative set to do this. So this was kind of interesting. So, and then, so this is quite different from the approach for partitions. So you have some another partial solutions, and then you define the equivalence. But we have some remaining question that, so you consider the L coloring of the graphs. And then the only row bound is that n to the small of k. But the naive algorithm is n to the 2 to the order of k, because you need to keep all the partitions for each colors. But we guess that this is optimal, but I don't know. Yeah, this maybe if you do something cleverly, then you can reduce this running time. Okay, thank you.